Only 3 minutes.
Yeah, it's all right. Hey, what's that supposed to mean? Tommy, write down this guy's name. We need to, yeah.
Can I write it down in like a Hoffman code?
Yeah, let's
Like
do that.
One bit encoding.
These rows are lovely to demonstrate range minimum queries. Now that we're messing with stuff. Cool. There's a bunch of things that are really nice today. I'm curious if there's enough time to get through all of them today. If not, then certainly the phylogenetic trees are doomed. But maybe it's doesn't take all that long, because some things you will know. I've done a bit of prep work in other parts. Okay, you remember the RMQ problem? We have to take that off first. That's where we left off. Is this array problem? You pre-process this array into a data structure that allows you to answer these queries where in a certain range is the minimum. And it's important here for this case, for this part that's to come, it's important that we just return the index where the minimum is and not the value. Because that means we can do this without knowing the actual values. All we need to know is the relative order. Okay. The second part about the ties, I think you can essentially assume that the values are distinct, and all that I'm going to say is it's going to sound a bit easier, and then the rest you can fix if needed. That's not as important. We essentially solved the problem for most parts already, the problem-specific nasty bit. You should remember the sparse table trick. We can essentially pre-compute many solutions, namely all those where the range that we're covering is a power of 2 long. Instead of all n squared queries, that's just n log n, so it's still a super linear space and pre-processing time. But if we do that, then we can answer queries in constant time. That was one option how to use that scheme. And the way this works is that we have always, whatever the range is, if you round down to the next smaller power of 2, there's going to be 2 ranges that cover that range and maybe overlap, but at least they fully cover the query range and tell you 2 candidates for the overall minimum. And if you have the array at query time at your disposal, you can go and check which is the actual minimum. All solutions will basically be built on that. Now, this I think we also discussed last time, but maybe let me start here again. We have with the sparse table solution, a solution in this notation that uses n log n pre-processing time and then gives us constant query time. We can just use this as a black box on an input with a smaller number of elements to bring the processing time down to linear. But fine, that doesn't solve the problem unless we are applying some problem-specific trick. And here what you can do is break the array conceptually into blocks of b elements each. We can choose b to be roughly logarithmic. Then the number of elements that we will use, namely just the minimum of each block. The number of block minima that we use is then n divided log n, so we can apply our linearithmic solution and still run in linear time. But that means we only can solve range min queries that have exact block boundaries. If we're lucky and someone asks for the range min from here to here, we can directly answer. But if someone asks between this non-aligned boundaries, we don't immediately get the answer from our light blue data structure. But we can at least we can solve RMQs on the block minima, that's right. What we can't fully do yet is solve general queries. but we can puzzle them together from at most 3 parts. There's going to be an interior range containing entire blocks. For that, we can use the light blue data structure to get which of all those block minima is the smallest. That's one candidate answer. And then we have 2 queries within blocks. And in the simple version, we just scan those in linear time. But it's linear in the length of this green part, which is at most the block size, so at most log n. Then the overall answer will be the minimum in this green part, the minimum in this green part, or the minimum of all the blue minima. Again, you compare these 3 candidates and give whatever is the smallest as the answer. Now we've seen how to do the dark blue one in constant time recursively, or using sparse tables on the block minima. And we could do just walk over the green part. That's where we left off. That gives us a linear pre-processing time, logarithmic query time solution. Probably a reasonable compromise in practice, but you can do better. And for showing you how you can do better, we need to work out what the combinatorial structure of this range min query problem is. And it turns out that there's a lovely, even bijective structure that corresponds to this problem. For that, let me first draw, this is just an array where the numbers are drawn as poles. The higher the thing, the bigger the number. And then you can visually think about range min queries as picking a certain range in the horizontal direction. And then let a line fall down from plus infinity until it hits one of the poles. Now, to make the pictures nicer, here I'm using max queries instead of min, just because it is nicer to draw poles of positive height. Of course, you can always flip all the comparisons around and make max into min or min into max. As long as you need just one of the 2, it doesn't matter which one you solved. You can always negate and get the other. But here, just to make the pictures nicer, everything's a range max now. Okay. Then again, so the picture is you take this bar and let it fall down until it hits the first pole, and that's your maximum, obviously. And the position where it hits that is the range max. Same definition, just explained visually. Now, how does that get a combinatorial structure? We could build a tree by taking the entire range over the entire array. So initially, I'm gonna kill this pen eventually. Still works. So you let a line covering the entire array sink down until it hits the first pole. And imagine it's a brutal pole. It just cuts the line in half. And so now the 2 left and right parts can sink individually down, independently of each other. So this one will indeed sink all the way down to this pole, whereas the other one will stop earlier. Okay? Whenever they hit a pole, they become split and independently keep falling down. Also, whenever I do this, I have a single first hit pole on the left and one on the right. Again, type breaking, take the leftmost if there's several. And these we connect to the previous whole array maximum with child links. So that's going to be the root of a binary tree with these 2 children. And I can recurse in that this line here, it used to be, from here to here. Now these are 2 independent lines that again sink down between these 2 tall poles. And so they keep going, and I get more and more nodes until this is the final picture. Okay? The way to get the tree is top down is the direction, and then you recurse on left and right whenever you have a maximum. That's a cute tree. What does that have to do with range maxima, though? If you look at a range like our red range here, there's going to be a leftmost and rightmost node, maybe in red, in the range. That's going to be these 2. Now, the range maximum is the lowest common ancestor of those two nodes in the tree. If you walk from those up to the root, at the very least at the root, they have to join paths. And they usually join a bit earlier, in this case here. And that node, this is again, the way I draw the trees here, the root has to be between those two. One way to see that is I've put the indices in the nodes here from left to right. These are the indices of the array. Then the tree we built happens to be binary search tree ordered. All the numbers on the left of a node are smaller than all the numbers, or smaller than the number in the node and smaller than all the numbers to the right. As in a binary search tree. It's obviously by construction because we just split in the middle. So you could also say these numbers in here are exactly the array indices or the in-order index in the tree. If you do an in-order traversal of this binary tree, whenever you see, when you visit a node, you mark it and increment a counter, then you get the same numbers. Okay, then the lowest common ancestor where the paths to these two nodes split for the first time has to be between those, because that's a point in the binary search tree. Think about it. It was a point where we decided that 6 is smaller than 9, but 14 is bigger. As long as they're on the same side, the paths don't branch out. Okay, maybe that's helping to visualize this a bit. So we've reduced the problem of range max queries to finding lowest common ancestors in binary trees. That may be useful or not. The way how we will use it, the way why it's useful for us, is primarily that since this is all about the tree, we don't need to know the heights of these poles anymore. All that counts is the topology of the tree. How many, what nodes are there? What are left and right children? We don't need the information of the numbers. And that's useful because there's fewer ways to build trees than to arrange numbers. Here's a Slido question where your task was to find where the minimum in this range lies. And there's going to be an array that tells you by numbers, but we can figure this out from the tree. Since we're such a small group, maybe we don't need the Slido question. And you can just quickly work it out. Volunteers. And remember, we start counting at 0. First, we need the in-order traversal of the tree to mark the nodes with their index, with these numbers, because otherwise I don't know what 1 and 5 means. In-order traversal starts at the root, then goes left as long as it can, and when that's no longer possible, when you return, then you visit the current node. Then you go recursively right. So I'm going left, 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 then I can no longer go left, so I come back, and this guy is the first one I visit, so that gets 0, right? Then I'm done with this subtree because right is empty, so I go back up. Now I'm done with left for this guy. Now I visit this node, gets the 1. Now I'm going right. And then again, I'm trying to go left as long as I can, but there's nothing. So I come back and then I'm at this node. I visit it, so it gets the next number. And so on and so forth, okay? The way I drew the trees, you could also say it's a sweep line from left to right. Whenever you hit the nodes, they get the next number. But this is because I drew them in the sensible way you should draw binary search trees. Okay, so we can identify the two nodes we're talking about, 1 and 5. In this chapter, I made the endpoints inclusive for no good reason other than lack of interest to change the pictures. So where's the range max? What do we have to do for these two? We have to find the lowest common ancestor. which of course you can do by walking up and seeing where the paths meet. So that's the guy at index 3. Okay, good. Here's one way how this array could look like that gives the same range max position. There we go. Now, how is this useful for our data structure? As I said before, we don't care about the actual values, just the tree counts. So let's count the trees and see how many different ways range max queries can look like. The good thing here is I didn't stress this carefully enough. It's really a bijection. If all you know about your array are the range max answers for all possible ranges, you can still reconstruct the Cartesian tree. And if you have the Cartesian tree, you can still reconstruct all the range maxes by definition because they're given in the tree by the lowest common ancestors. So the two are exactly equivalent, knowing all answers of range max queries or knowing the Cartesian tree of an array. That also means I can count binary trees to count how many different options I have to answer range max queries. For example, here is my small tree, and it has, was it eight nodes? There's only a certain number of different trees with 8 nodes that could be a Cartesian tree. And the precise answer are the Catalan numbers. If you have n nodes and you want to build a binary tree, then that's the precise answer how many you get. For example, if you said n to 3, then there's 5 options. There's this tree, there's a lopsided one, the symmetric one, and the balanced one. And hopefully if you insert 3, this works out. So it's 1/4 and then 6 choose 3, otherwise known as 6 factorial over 3 factorial, 3 factorial, and the 4. So you have the 6 factorial, 6 times 5 times 4. There's only the 6 times 5 left. The rest is cancelled with the 4 and one of the 3 factorials. And then there's another 3 factorial, which nicely works out to 6. So the answer is 5. Okay. Now that's if we were doing an intro to combinatorics class, we'd dwell more on this and how to compute it, but we don't actually care. All I want is an upper bound for the number of different trees. And this one's far easier to prove. One example, one way to prove that there's no more than 2 to the 2n trees of that shape, binary trees, is by giving an encoding for the trees using 2n bits. If that's possible and I can uniquely reconstruct the trees, then there can't be more trees than 2 to the 2n. And one way to do that is, for example, to say I'm going to write for every node in a depth-first traversal, has it got a left child? Yes, no. Does it have a right child? Yes, no. So that's one option. There's many others that are similar or slightly more useful for some purposes, but this is good enough. I guess I should say a pre-order traversal that we have. A clearly defined visiting order of the vertices. That clearly uses 2 bits per vertex, and if 2 trees differ, they have to differ at some point in the child links. What's less obvious maybe is that you can reconstruct the tree uniquely, but that's why it is important that you do a pre-order traversal, because then you can always keep track of which nodes still have open edge slots that we promised will be filled with children but haven't yet. And then because it's pre-order, depth first search, you know which one is the next one. With that knowledge that if we have n numbers, there's only 2 to the 2n, a few less options for how the range max or range min queries can look like, we can come back to our previous approach of taking a big array and breaking it into small blocks, using sparse tables for the minima of the blocks, and then doing something else for queries within one block. That's the intra-block queries. We'll have to be a little more restrictive with the block size than previously. Before I just said big O of log n is sufficient. Now I need to fix the constant. If I put it, for example, at a quarter, then 2 to the 2b, the number of Cartesian trees, or the upper bound, is just square root n. So I've picked my blocks with this b so small that there's only square root n different ways how all the possible range min queries inside this block can look like, because there's only so many such binary trees. Which means there's going to be, among all those n divided log n blocks that we have of our array, there's going to be a lot of blocks that do the same. They have the same local answers. Of course, for different values and shifted in index, but if you locally look just at this block, they're identical. They're equivalent in terms of all range min queries. And so we can use exhaustive tabulation, which you guys already know from the alignment chapter. We're doing exhaustive tabulation on these small blocks. We write down the type and then do an exhaustive table of all the types and all their queries. So for every possible tiny little Cartesian tree, we're just pre-computing the stupid way all n squared or b squared range min query answers. That's going to be a bit wasteful, but because b is so small, we don't care. And then on top of that, we just write down for every block which type it has. Now the extra trick why we can do this as a data structure is that we make sure these types are just numbers or bit strings. It's the same for a computer. So we can use them as an index in an array, and as a kind of quick way, constant time way to jump to the right type. Okay. How to compute this in the pre-processing is also not hard. You can do any representation of a Cartesian tree using 2b bits. For example, the one I've shown you, it's as long as it's just a code, that's good enough. And then we also fill, going through all possible trees. Say we have our little tree like this. Now I would have to write this down in binary, but let's spare us the details, or might as well do it. Okay, this has no left but one right. This has one right, left but no right, and this has nothing. So that's going to be the same. And then I have 3 choose 2 different range min queries, not so many. I could ask between 0 and 1. That's these 2 nodes. Where's the minimum? Well, this guy is on top, so the answer will be 0. If I ask for 0 and 2, say, and the same block type, I also get 0. And if I ask for 1 and 2, I get 2. Okay, so you can imagine we fill this for all possible trees of that small size and for all possible I and j, and we write down the answer. How much is this going to take us to do? The square root n block types, because b is so small, b squared combinations at most. So in still very, very little O of n time and space, we can fill this table. And with that, we found a solution for range min queries that, at least in theory, is perfect. There's nothing left really to say if you're looking at big O. It has linear time, pre-processing time, which you're gonna have to look at the array at some point, and constant time for the queries, where we do this decomposition in inter-block and intra-block queries. And for the green ones, the intra-block queries, we use this table lookup. By the way, this is also how you solve longest common extensions in strings, where we used back then for tandem repeats, etc. There was this thing left open, right? Okay. So essentially best possible in terms of these times. It's a bit more complicated than maybe you want to implement. It turns out this exhaustive tabulation technique is really bad in practice, because to make it feasible to really have the space to write down this exhaustive table, you cannot afford big blocks. They're really tiny. Like it depends how much really you have to store, but maybe a dozen or so is already the limit. And then the rest is still this dividing by 12 or so. In theory is log n. In practice is not such a big speed up. So oftentimes people choose slightly different implementations that have, in theory, a worse running time asymptotically, but tend to work better on current machines. But that aside, the theory problem's totally solved. And we can finally close this black box from last time. There's another thing we want to use this for. And again, I'm appealing to your memory that we left open some question about suffix arrays. Standard suffix arrays could already support some sort of string matching, but it wasn't quite up to speed in comparison with suffix trees. Let me try to remind you a bit. We can find a pattern in a string for which we've computed the suffix array, the leaf array, the starting positions of all the suffixes in the alphabetic order, where you're doing a binary search. So you have log n plus 2 in the worst case. Binary search uses that many comparisons. Checks if remember this was the suffix array, and then you start in the middle is the pattern that I'm looking for, smaller or bigger alphabetically than the suffix in the middle. And then you eventually cut the range in half recursively and so on. So after logarithmically many such questions, you're done. But each of these questions is a string comparison between the pattern and that suffix. And that could go on comparing many characters if they all share very long common prefixes. Again, the stupid example of having a text of all A's shows you the worst case here is indeed log n for the number of queries times m. Each could be scanning the entire pattern. Whereas suffix trees could do a lot better, assuming that the alphabet is constant or you're doing some trickery inside the nodes. You could even do it in constant time per character of the pattern. That's a far cry from this one. And if these enhanced suffix arrays claim to be a replacement for suffix trees, they should be able to do better. And they can. And we were missing this last piece, the rangemin queries, for a simple solution to do better than that. To motivate this, all we'll have to do is avoid comparing characters where we already know that they're going to be the same. But how, if you're forgetting everything in between? Unclear. So we have to remember something. And the invariant that we'll try to remember is precisely information about the longest common prefix we've seen in previous comparisons. So specifically, you're in your binary search at some point that you have two bounds that limit the range where P lies. So we have a suffix starting at A and a suffix starting at B that sandwich in the pattern in lexicographic order. And we remember what was the number of characters, the longest common prefix of this suffix starting at A and P, and similarly for B. And that's what we'll maintain also when we keep going in the binary search. The goal will be to avoid doing same character comparisons again. And what we'll use under the hood is that with range min queries, we can, from just the LCP array, these linear extra numbers between adjacent suffixes, we can find the longest common prefix of any two suffixes of the text. So this doesn't directly tell us what the longest common prefix with P is, but for any positions in the text, we can do it. And the answer is precisely the range min query of the LCP array in this range. And the reason, again, just graphically speaking, if there's some shared common part here, it might look like this. The characters that are shared from top to bottom are those up until the last one that is on the shortest common prefix in all of those. So that's the minimum in the LCP array. Okay, how can we use this? It turns out, essentially, you just do the obvious thing, but there's a few cases. So let me just illustrate it on an example. Here's our text from Hannah Band's Bananas Man from the suffix array example. And I'll cheat a little bit in that the indices for A and B that I'm going to pick are just chosen to illustrate the different cases. They're not really indices that can come up in a binary search because you would always cut things in half. Forgive me for that and just ignore it. Imagine the text is even longer and we're just zooming in on some bit. LA, again, longest common prefix between this upper, say here and here. There's some lower bound for the pattern, and we know how many characters agree between the pattern and this suffix, and similar for the upper bound. Immediately we know, because this is a range in the suffix tree, these are sorted strings, that the longest common prefix between this TM, the midpoint that we choose in the binary search, and the pattern has to be at least as big as the minimum of these two, because all the strings between these two, so we know P lies between those two, all the strings between A and B share these suffixes. Actually, the RMQ of the LCP could be bigger, but the pattern shares these characters with A and B if it's the minimum. So it shares it with all the strings in that range. That's enough. So we know a little bit about LM, and people claim in practice you may just stop at this. You do the binary search, you remember what the longest common prefix from the previous comparisons was, and you just skip whatever is the minimum of these two for the next comparison and keep comparing the characters from there. That's not optimal. So sometimes you do redundant comparisons if you do that. So you can do slightly better. And that's where the cases come in. Case 1. LA and LB are the same. An example is here. Well, the common prefix between the pattern, and the pattern will keep changing in the cases. I'm sorry about that. So here the pattern is Anna. And we've narrowed it down to this range. Happens to be all the strings that start with A, but that's pure coincidence. So all these strings here share the A as the first letter, and so does the pattern. In this case, we've maximally used what we know. That's all the knowledge we could extract from LA and LB. So we'll just start at M. This also shares the A. But then we'll start comparing with the next characters, and we'll find that N is bigger than A, so P has to go this way. The next round of binary searching moves A to M and keeps going. Note that because we explicitly compare this suffix at M and P, we also learn the actual value for LM, because we stopped comparing exactly when we've exhausted the same characters. That was the cleanest case. The other case is, well, if these are not the same, there's two symmetric cases, and let's just assume that LA is bigger. If you implement this, you'll need a second case where everything is mirrored. And this case, unfortunately, splits into three subcases. All the examples will have the property that there's a longer common prefix between the pattern and A than the pattern and B. Here it's LA is 1 and LB is 0, right? And on top of that, here we have that the longest common prefix between TA and TM, so these two guys here. I'm running out of good colors, but let me use this light green for that. This is bigger than LA. They share more characters than P and LA. In that case, you can figure out that because P already disagreed with A, after here the first character, the second is larger. We know that it's larger because P has to be bigger than A, or at least as big as A, and we know they disagree, so bigger than A, bigger than the suffix starting at A. And we know that M has, up to this position, at least these two letters are the same as in A. So P will still disagree on this second letter and will still win over M. It's just, they're the same. We've done the same comparison, and we don't have to touch any characters. By just comparing the longest common prefix information, we already know what the outcome of this comparison will be. Okay. There's a symmetric case, which has almost the same meaning. In this case, there's a longest common prefix between the pattern, or it's even more, right? Almost found the string, but not quite. We also have some overlap with B, but just two letters. So again, we're still in case 2, where LA is bigger than LB. This is something like 7, this is 2. But then we also have the longest common prefix between A and M, which is the... And in this case, the green part is shorter than the blue part. Well, what we know is that the pattern agrees with A for a lot of characters and then eventually is bigger. If M shares the same characters here and then is bigger than what A had, it must also be bigger than what P had, because they're the same. Right? The decision for the comparison is done after looking at the first 4 characters, and the first 4 characters of P and A are the same. So of course, the comparison between M and A and M and P has the same outcome. Again, no comparisons of actual characters needed. Last case, pinky promise, is this one, where these two are the same. And then again, we have to do some comparisons. Let me mark down again what is equal. So we have 3 here and 2. And now the longest common prefix between A and M is also 3, which means we've maximally exhausted our current knowledge. We can't deduce more about the order where P goes from the prefixes that we looked at. So we have to compare the next characters from here onwards. And the next character already decides P is going to be bigger, smaller than M. So it'll have to go here. We report that we didn't find it, whatever comes after the binary search. Okay. Yeah, in all cases, you can figure out that you've learned LM. Needs a different argument in the 3 cases, but you can work it out. And you can go through the cases again and verify that whenever you're doing a comparison that comes out as equal, that character in P you're not going to touch again. You're not going to compare that more than once in one recursive step of the of the binary search, and you always make progress. So over the entire binary search, you touch all the characters in P a constant time each. That's why the overall search time is this m plus log n. It's not exactly equal to the suffix tree time, where you could get rid of this plus log n, but it's good enough, because either, I mean, log n is fairly small. The only real problem previously was if m is relatively big, and then in this case, m dominates. That was essentially the last missing piece in our discussion of enhanced suffix arrays and how they can support the operations of a suffix tree without storing this full tree structure. All the other bits we've also filled now with the arrangement queries. And so you've essentially seen how to replace suffix trees entirely just using these array-based techniques. Okay. What next? We still need, for all of this to work, the text explicitly written out. And we need this in various places. Certainly here for the last part, you were doing comparisons with certain characters in the text, so you need the text. There's the notion of a self-index, which is an index on a text that helps us search, but doesn't need the text. It's a bit crazy, like if a book had only the index and the rest is thrown away. You obviously need to grow the index a bit by that then. In a more technical term, we can, if we don't have to explicitly store the text so that we can jump to specific characters, we might get away with storing it in compressed space, but still work on it, still search in it. And indeed, that's possible. That's up next. You want to guys take a short break? It's precisely 45. Like, couldn't have planned it better. Apart from the fact that the second half is probably longer. This is this new weird bug in Xornal that popped up now, that it always duplicates pages first, and you have to reconfigure the new page template.
So I want to tell you something funny about this RMQ stuff. In practice, the biggest problem with the sparse table implementation of RMQ is if you will hold the array the wrong way. If you have a 2D table, right?
Ah, I see.
If you hold it
Sure.
first the position, then the levels, this is very slow because of cache stuff. But if you hold it first
the length,
levels, then by position,
that makes sense.
Works. Second, another interesting thing, it's not practical, right? This linear time solution.
Yeah, not as it's stated, yeah.
However, there's a very nice n-log star of n solution for offline RMQ.
Ah, I see, sure.
So if you have offline RMQ, you reduce this to offline.
You know what? That makes a nice exercise problem, unless people know this, and I don't think it's so well known.
Okay, should I not say anything then? Can you be trusted?
There's two options. You can either tell them and hope that they process this in 3 minutes, and then we ask a question where they apply it to something, or we do a more basic problem where they essentially have to design this solution with a little bit of nudging.
Okay, so I won't say anything.
I think it's outside of competitive programming, I'm not sure this is so well known. It's of course like, sure, Tarjan and whatever.
Yes.
I can say that name. If they're gonna read all Tarjan papers to solve the exercise problem, it's fine.
I mean, it might even be good for them.
For sure, yeah.
No, but I mean, you see, this other solution is actually very fast in practice. Like offline, that it actually moves like an.
Is Logstar the best? No, right? You can do inverse Ackermann, but
yeah,
with
I'm talking about the inverse Ackermann, whatever.
Yeah.
Logstar is the way I usually say it. Who cares? 4 versus 5, like.
Sure. No, I think they're the same algorithm, right?
Yeah.
Just Logstar was the first analysis. and then the
Yeah, so
alpha
the
is.
analysis I know how to do, or I knew at least once. The inverse Ackermann I have never learned how to do.
And you're also not doing the actual inverse Ackermann, but the halving in practice.
Yeah, but the halving works.
I'm not sure if that's.
Somewhere it's the same.
Oh, it's not the same. It might have the same running time. This I don't know.
Oh, I've read somewhere that's the same running time. But okay, in practice, the halving is way faster as well. So like, my point is, if you actually want this thing to run fast, you do it this way. But also,
for finite input sizes, right? Yeah.
Also, the way I knew how to do the second part of reduction is a bit different from what you said. This auto reduction from RMQ to search tree, from search tree to RMQ. Because
you can phrase it in different ways.
The way I knew is you do the Euler.
Yeah, Euler Tor.
Of the graph.
Of the tree.
Where it goes
that's right.
Times.
It's a bit wasteful. You lose a factor too.
I agree with you.
You're excused because the first papers that used this also had precisely this factor too.
Yeah. So I realized as I was looking at what you were saying that obviously you're right.
This cuter.
Obviously better, but I never actually,
When I first saw about this, I immediately said, obvious. This is just how you do it. Encode the binary tree in such a way. I used the bounds parenthesis. But this, in the data structures community, this wasn't so well known. You can, how do you do bounds parenthesis for a binary tree? You encode the left tree recursively, enclose it, and put the right tree behind it.
Yeah.
They were always thinking in terms of having parentheses around yourself and then your children recursively next to each other, but you can't do that in a binary tree because then you can't distinguish left and right single child.
Yeah, that's what I was
thinking as well. Somehow this is where they got trapped and lost. It's so funny.
When I first saw this thing, I thought, surely it can't be Catalan. It has to be Catalan.
No, yes. And there they describe a clever scheme that encodes the RNQ solutions in a number that turns out to be Catalan bounded because they turned out to find the same result, but they also didn't know this simple trick with the tree encoding. Very funny. Yeah. Okay, guys, ready for the real stuff. I think the rest of this unit is admittedly a bit less detailed, and some things are a bit more. Here's an example that shows how this works, and there's details that have gaps that need filling, but I felt there's more benefit in seeing the overall solution as opposed to every minute detail of the steps in between. It's kind of just a warning up front. And of course, we can discuss details in some other occasion, maybe some tutorial where we have leftover time or whatever else, oral exams or, you're of course not expected to know more than what I told you here. To get to the self-indexes, I'll have to train myself. Always have Götz Gräfe in my ear now when I say indices. Hard to forget. Before we can get to the self-indexes, we have to take a little detour, introduce this cool trick or transformation on text, the Burroughs-Wheeler transform, that the coolest of these self-indexes are built on. For a moment, it will look like it has nothing to do with text indexing. But again, like for RMQ, bear with me for a little bit. It'll come back. For everything we've done so far, we need the text and essentially in fast memory to do random access on the characters. And that can be a problem. For a single genome these days is a bit questionable if, 4 GB of main memory is not a big deal. If you think for the next thing, the NHS, the National Health Service in the UK, has recently collected, I think they've done 100,000 genomes. So multiply your 4 GB with 100,000 and you do get into trouble for main memory unless you're maybe the beefiest of beefy machines with very expensive can still hold that in one place, but it's getting very questionable. So you want to compress, and then that means you can't explicitly store the text anymore. That's my point. Take it for that. And so we can't use the enhanced suffix array as is. That seems inevitable as long as we want to reconstruct the text, except we can compress, right? Okay. Maybe this is useful to keep for terminology. People call this the encoding model. We want to answer queries about some piece of data, but we're allowed to, we have to keep essentially the data around to be able to answer these queries, because the queries themselves allow you to reconstruct the data itself. But we don't need to keep the data in the original form. We're allowed to encode it in some new way. That's what this self-index is also going to do. Okay, general like end of advertisement, but the research field that talks about these things is computing over compressed data in a more general sense, where data could be other things than text. In the interest of time, let me move on to the definitions. The first thing we need is a cyclic shift of a text. So here's a text, here's a cyclic shift, where all that has happened is take a bunch of characters and move them at the end, to the end of the string. And you can do this with any number of characters. In general, as this example maybe shows, you can not necessarily reconstruct where you came from unless you know by how many characters you shifted. But standard trick that we've applied in all of the previous chapters was append a unique character at the end of word character. And then, of course, you can recover from any cyclic string what the original string was, because you keep shifting until this thing is at the end. That's the setup. Now, the Burrows-Wheeler transform, this mysterious text transformation, works as follows. In a text with this end of word marker, you build all the cyclic shifts. There's going to be exactly n plus one of them if the text had n characters plus the new one. Then we sort those lexicographically, and then comes the weird and crazy stuff. Take the last column, the last character of all the cyclic shifts, and you read that top to bottom in sorted order. That's the BWT. Example, here's some obscure text. Here are all the cyclic shifts. You see that the $ walks all the way to the left. And then you sort these alphabetically, which gives you this. I'm here again assuming $ comes before all the other characters, and the rest is just the ASCII order. And the last column in this arrangement is the BWT. So you turn this text into this. Why on earth that should be useful, we'll come to soon. A quick observation, because you've wrote down every cyclic shift exactly once. You've written down every shift exactly once. Every character in the text occurs in every column exactly once. For example, the first A occurs in the first column here at the top, because that's where the first guy was. In the second column, it appears exactly down here, and so on and so forth. And that's true after sorting, because you're just swapping rows around. In particular, also, the last column consists of one copy from every index in the text. In other words, the BWT is a permutation of the characters of the input text. It's going to be the same number of the same characters, but in a weird jumbled order. That's just from the construction. Let's talk about how we can find this, because it involves sorting, and we've talked about sorting strings already a good deal. Indeed, it is nothing but suffix sorting if you look at it from the right perspective. And the reason is that these $ symbols mean never ever are you going to look in a comparison at the characters after them. Because the $ symbol is unique, it occurs exactly once in each column. So whenever the comparison supposedly reaches the dollar symbol, you're not going to look after because that one decides the comparisons for sure. So between any two strings, if you compare them, at the very last with the first of the dollars, you know which is smaller, which is bigger. The dollar decides. That was not a political statement of currencies. So that means if you sort the suffixes, then that there's these cyclic shifts there is just a kind of management. You're dragging some baggage around, but they don't influence the sort order. In particular, you can reconstruct the Burrs-Wheeler transform just from the suffix array. If you have the suffix array L, then the ith character in the Burrs-Wheeler transform is obtained by taking whatever the ith suffix is, but then the previous character, because again, this is wraparound, right? A cyclic shift. You obtain where this character, this character here is the one that comes before the character here. That's exactly the example where the wraparound is needed is modulo n. So the -1 needs to be modulo n. N+1. If you have the suffix array, you can construct the Burrs-Wheeler transform from it easily. And we know how to compute the suffix array in linear time. So at least in principle, if we're okay with having this intermediate suffix array, then we can compute the Burrs-Wheeler transform efficiently. So that part's done. Again, if you were to use this in practice, there's good libraries that do this directly, also avoiding the extra working memory. These are interesting methods, but let's not get into this here. A tiny detour, just motivating why the BWT is at least historically coming from text compression and not data structures. It turns out that for typical kinds of texts, this BWT is more compressible than the original text in a specific technical sense. And the reason for that is that sorting groups by context. Specifically, the character here in the last column is whatever precedes these characters. And so we have the example with LF. If you look at the suffixes that start with LF, these three, all of the occurrences of LF in our original text started or were preceded with an A because it was Alf eats alfalfa. Proper English sentence, right? So these three A's here are lumped together because they are much more likely, in this case 100% likely, if after them comes LF. In other words, sometimes it's not as extreme, but you could say if you look at these, all the suffixes that start with an A, then the corresponding characters here are the things that come before an A. And usually that is giving you some information. There's in English text, there's some letter combinations that are much more frequent than others. If you know what comes after a character, you know some information about the character itself. It gives you a skewed distribution. And then these characters in the BWT will locally follow this distribution. Okay. So BWT groups the characters by their context. And that specifically means if a character can be predicted with less entropy than otherwise from what follows after it, then the BWT will have locally a low entropy among the characters. There'll be regions where you see mostly A's or regions where you see mostly L's, these kind of things. In the compression context, you can then use another transformation that turns this locally low entropy into globally low entropy by something like a difference transform, conceptually. The method is different. For those of you who've seen it, you will know what I mean, but you could maybe imagine that you locally rename the letters so that this locally low entropy becomes a global thing that you can then exploit with standard tricks like Huffman codes, for example. We're not going to do that here. This is just the historical context is entirely from text compression. And it turns out the BWT has a few other very useful properties that are certainly related to this, but are in a way stronger or more useful. Just to illustrate, this kind of grouping becomes more powerful if you have a bigger text, because then you have more things that share context. And these are always grouped by the sorting. So here's some text that's a bit repetitive, but to make it small enough for the slide, maybe that's fair. And what you see is that there's many runs of the same character in the BWT. And that is something you typically see with natural language text. Indeed, you can even prove. We're not going to do it. I'm just citing the results. If you take the BWT and you run length compress it, which is, I'm just going to write down here, this is 7 times an H. Then comes 2 times an A, 2 times a V, 4 times a space. That's all I'm doing. And I call the number of such runs that I have to do when I write down the BWT R. Then here's some example from previously. Here R would be 12, whereas the length of text was 17. So we saved a little bit by having these runs here. In this bigger example, we even get to half of the length of the text. And this is quite typical to continue. And what you can prove is that this number of runs is related to what you get from a Lempel-Ziff compression method. Again, if you don't know what Lempel-Ziff 77 is, it's not important. It's a way to use essentially local redundancy in that you have phrases that occur again, substrings that are repeated. And this is about the best method to exploit that in some sense. If that is then the size of the text in this compression, then this R from the BWT is only slightly bigger. That's one reason why it works so well in compression. That's all I'm going to say about compression. That's kind of the historical context where BWT first arose, but it's not the main application these days. There's one important thing we haven't talked about, which is how to get back to the original text. I told you it's used for compression, and we want to build a self-index based on it. It would be quite useful if we could get the text back. And normally, if you take a list and sort it, there's no way to get back to the unsorted list, right? This is a destructive operation in some sense. At least it loses entropy in that sense. Well, for the BWT, that's not the case. We can get the text back. Let me first show you how and not tell you yet why, because I think the aha moment is bigger that way. So here's the magic solution. You take your BWT. Now you build this curious, these objects of pairs of a character and a number. The first is the character at the BWT at position R, and the second is that position. Then you stably sort those pairs, meaning first by the character and then breaking ties by the number. And then you use this as essentially a linked list to jump through the text. Let me show you on an example how this works. Here's the BWT of some text. Unless you're a genius on these things, maybe it's hard to see what the original text was. Maybe you can guess, or maybe you've seen the example before, or you're a genius, one of the three options. Yeah. Yeah. Here's the D. Every magician needs a trick, so the show starts with doing these pairs. That's that construction. Then we sort them. And this third part, I think, needs an explanation that is really clearest in the example. We know where to start because the $sign has to be at the end. So we start where we find the $. And then the main iteration starts. Follow the pointer that's given in this current pair. So the 3 tells you to go to position 3. output what you find there in the first position and then keep going. So we output the A as the first letter in the clear text in the original string and follow the pointer 7 to go to the next position. That tells us to write a B, then 11 goes down here and so on. And you jump wildly through the text. And at some point you have to stop, right? How do you know how to stop? I guess there's two options. You know the total number of characters, so you could count. But you also know when to stop when you reach the dollar symbol. Abracadabra. Why does this work? First of all, the running time of this is pretty good. You can do the sorting in linear time because it's small integers. What we have to do to decode the BWT consists of always two steps. And let me show you the example again with kind of the black cloak drawn, and you can see what's underneath. This is the BWT. Here's our D and the sorted Ds. We know where to start with the dollar. That was here the 3, which means we're currently looking at this row in the BWT in this matrix. Now the first character, the dollar is the last character. What we'd really like is the first character in the text, which is in that same row, the entry in the first column. Now the first column is special. As you also see in the example, it has to be the characters in the text, which is the characters in the BWT in sorted order. Which means we can easily reconstruct this from the BWT without extra knowledge, just sort the characters. Which is exactly what we've done as part of the decoding by sorting the pairs, right? So when this in the BWT was at position 3 or still is at position 3, after the sorting, it remembers that position 3. But now going to this character here at position 3 means in the sorted list of the characters go to index 3. So this A here is the same A as this here, because we took it from there, essentially. It's also another A. This A also occurs somewhere on the right. So I'm jumping a bit ahead of my slides. We need two steps. The first is what I've just illustrated. We're in some column, in some row, and we want to jump to the same character in the first column. That was the part that just needed the letters sorted. Then we also need to find where this A occurs in the BWT to do the next step. For the dollar, this was a bit easier because there's a unique dollar, so you know where it is. For A, that's not the case. There's 5 A's. What else? 5 A's in the whole string. So how should we know which of the A's on the right is this A? And we need to pick the right one, otherwise it will break. Now, the trick is that, okay, this first one we worked out by sorting the characters. For the second part, we have to use that these guys are sorted. So there's these 5 A's here, there's these 5 A's here. Surely nothing is lost, but we need the mapping. For that, look at what follows the A in these 5 suffixes. And I've tried to color this in 5 different colors that show a sorted order. They're just what follows the A in alphabetic order. Now, if you take the A away and you go to the cyclic rotation 1 character shifted, these A's were all tied, so the comparisons were all decided by what followed the A. If I take away the A, if I take the A away, all these 5 suffixes or cyclic rotations, they will be sorted in the same way, because the dollar following the A here is still smaller than everything that followed A here. So this dollar is smaller than all these guys. And the same for the others. So these colors after the A and the colors without the A remain in the same sorted order. Has to be. And that means this A is mapped to the first A here, the second A is mapped to the second here, third to third, and so on. That's why we can decode, because it means that this A here, the third in the sorted order, I know that it's the third because I know the position and number of characters. So we also know it has to be the third A here that we have to go to. Okay. The decoding algorithm does this kind of automatically by keeping track of the indices. But the reason why it works needs the argument. I've explained this in detail here again because this trick is precisely what we'll use for the data structures in two different ways. Number one is we can actually decode substrings of the text starting at any position and for as many characters as we feel like. So if we want to find where, I don't know, in our example, say we want to find, I'm making this up. That's a bit too short. Let's say 5 to 8, but exclusive. So these three characters, T, 5, 6, 7, how would we find them? Once we know where to start, if we know a position in the BWT, we can do the same steps, jump to the character here, find where that is, and so on. But how do we know where to start? That's indeed not possible with just the BWT. We need something else. But we have a structure that tells us where in the BWT index 5 lands, because that's the same as where a corresponding suffix in the sorted order is. That's the rank array. So T5 is the character here. Now we don't know this guy, right? You have to imagine we can't see this. But what we do know is the entry in the rank array, which tells us this suffix that starts at position 5 is at position 1, at index 1 in the sorted order here, which means also at index 1 in the BWT is the first character here. That it's the row where we start. It's not that n is the character we're looking for. We start, same as before with the dollar, we start one character before where we want to read. And from here on, we do the same decoding step as for BWT inverse. We could use the same sorted D. So it tells us we should go to position 5 here. So we output a B. Then we should go to position 2. That's here. So we output an A. Then we go to position 7. So we output an N. And that's almost right, except that I missed the A from here, right? Did I make a mistake in the decoding? I didn't output the A here when I arrived. I said we'll land here. We're not using the N, but I have to use the A. I was looking at the wrong column. Okay. So off by ones are tricky, but the decoding step, once you know where to start, follows the same steps as the inverse BWT. But we now have a data structure where we can store the text in some potentially smaller space form, but we can still read out any substring of the text. What we need for that was a way to do this. Find the ith character in the sorted order in the first column of the matrix for BWT, and then jump to the corresponding occurrence in the BWT. That was the two operations that we needed, and the sorted pairs was one way to do it. Okay, with this we can build random access in the BWT. I've basically shown you how. What I didn't tell you is how to get this sorted D to use up less space. The way we described it here for the inverse BWT is not quite how you want to do it if you care about the space, because it would, for one thing, in the first column store the text symbols explicitly again, and then you need, the second one is a lot of indices. However, there's a data structure that we're not going to get into how it works. We'll just use the result. That does exactly the right queries. And that's rank and select on sequences. Look at text like ours here, it has a bunch of characters that occur, A, B, and N in this case. And I can define a rank query, which is in some prefix, say up to position 4. What is the number of A's in that prefix? 2. Or what is the number of B's in that prefix? Well, just 1. And what's the number of N's in that prefix? Also 1. That's the queries I can ask. I can also do the kind of inverse query if you tell me I want A's, but I want the second A in the text. What's the position of the second A in the text? Then this entry tells me it's at position 3, which is here. Okay. These are clearly useful operations because formally defined here. I'll appeal to the example instead. We can use those to build the two operations to decode the BWT from just these rank and select operations. The second one is particularly easy. If you want the rth occurrence of a character C, that's exactly a select query. And if you want the first part, where does a certain occurrence, the ith character in the sorted order of the ith occurrence of a certain character appear in the sorted version of the BWT, that's almost a rank query, but you have to offset it with all the characters that come before you in the alphabet. So formally you take if you just need the character, you just need to find in this array that stores how many characters are alphabetically smaller than you, the right index. You can also get the actual occurrence of the character. We don't actually need that, that's right. We just need to read out the character in the sorted position. So if you can do rank and select on sequences, you can simulate what we've done with these sorted pairs, the sorted D. And without explaining how this works, there's a data structure called the wavelet trees. In other contexts, some of you have discussed this, which supports exactly these operations and uses n log sigma bits of space at most. You can actually do a bit better. But even to state the guarantee would lead us further away than I want to go at this point. It happens to be possible with that data structure without extra cost to support precisely the queries we need. I don't need to do this offsetting trick here. You can also, for a character, define this sigma rank, which is the normal rank, but plus all the occurrences of characters that precede this character in the alphabet. So for all C prime less than C in the alphabet, you add how many occurrences they have in the total text. That turns out to be exactly what we need, and wavelet trees can support that essentially natively, if you like. So you don't even have to puzzle that together separately. Sadly, we'll have to leave it with a promise that this somehow works. If you want to see how, then you need to come back next term. Now I committed to doing that, I guess. We'll leave it for the rest of today with just this black box, that there's a magic way, the wavelet tree, to store a string, in our case, the Burrs-Wheeler transform, that can answer these rank and select queries. The running time, by the way, is big O of log sigma. So if you think about a bioinformatics context, the alphabet will be small. Sigma is 4 or maybe 20 for proteins. And so this is really fast. Okay, if we store the Burrs-Wheeler transform as a wavelet tree, then we can reconstruct any characters from the text just from that in L log sigma time, if we know where to start. So remember, we needed the rank array to do that. Now, if you invested all this effort to compress the BWT, you don't want to spend another n log n bits to write down this bloody rank array. But you can have a simple trade-off here, that you only store every tth entry of the rank array. So you can reduce the space by a factor t and keep decoding for a bit longer. So in particular, you can, if you know you want to start at position I, then you can't get the suffix there, but you can start a little earlier, round down to the next nearest I divided t, and start decoding from there. There's going to be at most t characters that you decoded as extra effort, but then you can reduce the space. That's a simple trick to get some reasonable space, and this is a practical alternative that people use. With that, we have essentially a data structure that you could say is a locally decodable Burrs-Wheeler transform. We don't need the text anymore. We can reconstruct the text on demand whenever we need it. And you can use that wavelet trees can be further compressed, which again, I know in this context, I haven't told you how, and so you can just say, wow, okay, I'm going to believe this. That's all I can offer. See you next term if you want. There's one last step, and then we're done with the indexes. We can't search in this yet. It's a way to compress the text, and you can locally decode. That's lovely. We did want to have a data structure for read mapping, if you remember, from all that time back. We started with the bioinformatics motivation of aligning small reads of DNA to the reference genome. We can't do that with that BWT, so that's not quite there yet. Turns out you can with a slightly different trick, and this is the most beautiful idea in this part. So I hope we can get it across in 5 minutes. It's actually an easy trick. You just search the pattern backwards, and then you can use what the suffix array and BWT structure already provides you to narrow down the search in a very natural way. We could already do a binary search, and that's all right, but that only works if we have the suffix array. Now, with BWT alone, that doesn't seem to work, but we could do, you could say, a backwards radix search, fancy name for something I haven't shown you. So let's just see an example instead. Say we're looking for this small pattern Anna, which is a bad choice because it's a palindrome, but I wanted a small example. Initially, we know nothing, so the range where we could be looking is all the suffixes, so all the positions in the BWT. What we really have is just the BWT for now, and maybe that's all for the first step. Now, suppose we start with the last A. We try to find occurrences of this pattern that at least have this last A. It has to be suffixes that have an A here, and then we go further to the left. So the end positions here we know are in that range in the sorted order, because these are all the suffixes that start with an A. That's all occurrences of A, full stop. That's not what we need in total, but for the last character, that's fine. Now we include the second to last character. And that means if this is the occurrence of A, the previous character from there is wrap around the position in the BWT where there's an N. In this case, there's only these 2 N's. There could be several more, but I can take the first and last and shrink the interval that I'm searching in to everything that starts with AN. Because again, in the sorted order, these have to be adjacent. Now, note that there's 3 things that start with AN here. And if I take this N and look at where it points, so I need to find the second N and the third N in the occurrence. Sorry. AN, we need NA, not AN. There's 3 N's down here, but only 2 that start with NA. What I do is, this is the second N in the BWT. It has to map to the second N in the sorted order. And same for this guy, this maps to the last N. So I know I can move my range if I look at NA as the pattern, I can move that from these 4 things to these 2 positions. And that's a range that contains everything that starts with NA. And I could do this from just again using the same rank and select queries on the BWT. In our case, the pattern goes on. So we have an A in front. So we check in the Burrs-Wheeler transform the range that we currently have highlighted. These are all A's. So I pick the first and the last A. It's these 2 in only. And that is the first, second, the third, and fourth A in the sorted order, which corresponds to these 2 guys. Okay. So here this maps to these 2 positions, and that's my interval of occurrences of the pattern, because I've reached the end of the pattern, the beginning of the pattern now. So I know in sorted order, I have occurrences of this pattern at ranks 3 and 4, and I haven't done any binary search. I've just done steps through the pattern, and each step was fairly fast, just this rank and select queries log sigma, no log n, no n involved and anywhere. There's only one catch. I don't know where these occurrences in the text are. For that, I need these 2 entries in the leaf array, in the suffix array. Ignoring that part, here's more carefully written code that does this backward step. It's doing the same thing. You initially start with the interval of everything that starts with the last character of the pattern. And then in each step, you look at the character of the pattern 1 position to the left. And you find in that current range, the first and last occurrence of that character in the BWT, and map that back to the sorted column. Okay. And once you're done through all the pattern, you can return this interval of ranks. These are all the ranks where if your rank is in there, the entry in the suffix array would give you the starting position. So the only thing that's missing is to do the same sampling trick for the suffix array. Previously we said we used the rank array and store every teeth. Here we're doing essentially the same trick for the suffix array. And then for each of these ranks in the interval, decoding a bit more until we reach an entry where we have the starting position stored, we can report where all these occurrences in the text are. And the total time for this is m times log sigma. Again, sigma tiny in our case. So it's essentially like in the suffix tree, just m, to find, for example, how many occurrences there are in the text. And then here, this oc is the number of occurrences. If you want to find out where these are in the text, the starting indices, then for each of them, you have to continue maybe for t more steps and read the corresponding value of the suffix array. Oof, okay, that's it. That thing is called the FM index and is at the root of widely used tools for doing read mapping. If you have single genomes, it's still essentially state of the art. There's a bit of a gap between what I've shown you and the FM index and the read mapping because we still need to do inexact searches. This is all for precise string matching, but we've talked a little bit about how to get from there to the inexact matches. The FM index was one of the first of these compressed self-indexes and still widely used. You can prove with the right wavelet tree representation that it compresses the text in something better than a Huffman coding trick, kth order empirical entropy, for those who know, if not, forget it. And here's the reference for the read mapping tool that's based on it. And this is an area that's still somewhat active because the data keeps growing and evolving. Even that trick is not good enough anymore. For these 100,000 genome collections, you need to do even more aggressive compression. And there's follow-up things on that, but we'll leave it with that. What's also not kind of a theory question might be, can you do all the operations that you have in a suffix tree using just the BWT? In particular, we're missing the LCP array so far. For just the string matching, you didn't need it. For all the other fancy things that a suffix or enhanced suffix array can do, we don't know yet if that's doable without extra space for these self-indexes. Good. Let's leave it there. Just about. Sorry, the last part was maybe a bit rushed. I lied a bit here in this part. I didn't explain. You can't just take every teeth index. You're taking every teeth value, so it's a bit annoying to properly define this, but you can do it as described on the slides. I don't know if you read the slides. I didn't speak about it. The slides don't lie, I think.
Why now?
Why now? After this, it would have been useful for the seminar.
Yeah.
I want to ask about exam, the second exam.